Hello. Today's lesson we're going to learn about something called the central limit theorem. And to learn about it, we're going to look at this little applet that we have here. Now, the central limit theorem might be the most important theorem in all of statistics, or an intro class anyway. Now, what it says is it talks about what happens in distributions. So if our sampling, if our population is normal, like it is here, if I want to take, say, an n of 2, so I'm going to take two values, and then I find the mean of it, this right here is starting my sampling distribution. If I do it again, I got two more values, and the mean of that is over there. Two more values, and the mean, and so on. And this is how a sampling distribution is built. You just keep on taking two values and plotting the mean in the thing below. Now, if I, instead of doing one at a time, if I plot five at a time, it looks like this. Five more, and so on. You can see that the distribution looks like it's starting to be normal. Now, let's say if I, instead of doing five, if I do 10,000 data points, 10,000 data points will look like this, which is really close to a normal distribution. And it makes sense if the population is normal, the sampling distribution will be normal. Now, the things that are weird, though, is if it's a uniform distribution. If I take a sample, oh, I want to take a sample, and another sample, and another sample, on a uniform, it's not necessarily entirely normal. It kind of looks like it goes up and it goes down. Not necessarily normal as much as just like more bell-shaped or more triangular. And so this doesn't exactly make a normal distribution. But if I change this from, instead of taking 2, if I take a much higher number, if I animate this, I'm going to take 25 data pieces from our population. And then out of 25 of those, I'm going to drop one mean of that distribution. Then I do it again. And I get 25 data points. And then it will slowly drop another mean. Now, if we did this many, many times, we could do it 5 times, see what we get. 5 more, 10,000, 100,000. You can see this distribution looks very, very normal. Where when we took an n equals 2, it was not a normal distribution. It was more triangular. But as my n got bigger and bigger, the number of samples I'm taking out, it became, the means formed a normal distribution. Now let's look if it's skewed. If I get a sample of 2 and animate it, I have that. And if I get 10,000 of them, it still will have a skew to the right. However, if I have a big number, like 25, if I animate that, that's going to take a long time. Let's just go cut to the chase. If I put 100,000, you can see it makes a normal distribution, even though the population distribution is not normal. It's skewed quite a bit. Now let's do something even crazier. This one still amazes me. So if I want to make my own parent population, if I do something like this, there's a gap in the data, comes down, and then it comes up there. So this is a weird distribution. If I went to n equals 2 and animated it, and if I did 100,000, our sampling distribution is just kind of all over the board. Now, if I switch that to a higher number, animate it, you'd see 25 things drop. But if I do 10,000, it's going to be a nice normal distribution, which is just amazing. This is why normal distributions are so important to statistics, because the sampling distributions become normal as n gets higher and higher. So our central limit theorem says if we draw an SRS from a population uh, with a mean of mu and a standard deviation, when n is large, the sampling distribution for x bar is close to a normal distribution, and the mean of that distribution is mu, and the standard deviation is sigma over the square root of n, just like we learned previously. Uh, and when it says uh, large, what we're looking for is we want our sample to be greater than or equal to 30. If our sample is greater than or equal to 30, we're very comfortable in knowing that this sampling distribution is going to be normal or approximately normal.